Kurt, you've got some company.
Hey, Kurt, I've got a philosophical question for you.
Hey, how's it going?
Good. On your MDS data for that data set where you're comparing different number of analyses on the same sample, essentially, and those are relative to a sample. What does that data look like if you compare it to like a dissimilar sample?
Oh, it basically that box, the axes on that box would it'd be, I could show it at the end of the course if you like.
Yeah, I mean, without looking at other samples, yeah, I know the matrix or the box would explode, but like right now, like the 120 samples or analyses or sessions, whatever you want to call it, look very different than the others. But like in space with different samples, how different would it look from the 1200-2 sample?
Maybe I'm not following the question.
I think what you'd get is you'd get your very different sample sitting here, and you'd get a cluster of the 120, 300, 600, 1200. There would be the same kind of separation of those, but they would all sit in a cluster relative to bananas out here.
Yeah, I guess like philosophically, I'm just thinking about, practical applications of this. How much of an impact does 1200 analyses have versus 120 when you're comparing different samples to each other?
Yeah, I think it really comes down, it's always data dependent, sample dependent, right? That's why for all the routines that we can do, these rapid analyses, live reduction is kind of the next step, right? So if you're analyzing, and you're not learning anything new about that sample, then yeah, stop it at 100, stop it at 300. Because you don't need 1200 or 1000 for every sample, right? If it's super complex, you might. I mean, if you look at some of Alex Pullen's recent work, Mauricio Ibanez Mejia's work, they've, I think, done a good job of demonstrating that not all of them need it, big, like large sample size, but oftentimes they do. That's why we picked the sample we did, because we knew it was complex from George's earlier work with Dickinson, and then Alex Pullen's work with George, and yeah. Sample complexity, I think, is where this is really a benefit. I don't know if that answered your question.
Yeah, good enough. Thanks.
All right, I think we're ready to jump into something completely different. This is not going to be geochronology, although time is an important part of how this system works. I'll warn you, it starts off kind of simple and kind of easy, and it kind of sneaks up on you and gets a little bit more difficult. And then at the end, when you have to interpret some data, which Sarah's going to help us with in a few minutes, it's like, oh no, it's like, how did that work again? Why do these things move up and down in epsilon space? So fasten your chin strap, pay attention, follow as we go from simple to more complicated, and stop me in case I make a step that you don't quite follow. And let's work through this. So we're talking about lutetium, hafnium isotope systems, and the real action is hafnium-176 to hafnium-177. That's the isotope ratio that we're really interested in. And the reason that ratio varies in nature is because 176 hafnium is the daughter product of lutetium-176. So we need to talk about both of those. And then in terms of how you do these measurements, we also need to look at ytterbium, because there's an isotope of ytterbium-176 that is indistinguishable from hafnium and lutetium. So these guys, 176, your mass spectrometer, it only knows it's 176. It doesn't know if it's hafnium or lutetium and ytterbium, but somehow you need to do a subtraction to get rid of ytterbium, get rid of lutetium, so that you're just comparing hafnium-176 with 177. Okay, so that's what we're trying to do. The good news is that it's a pretty rich playing field here. We've got blue, all the different isotopes of hafnium. These are stable in nature, except 176. This is the daughter product of lutetium-176. For lutetium, we've got a stable isotope and a parent here that decays. And then ytterbium here, these are all stable in nature. Okay, so those are the different isotope systems we'll be talking about during the day today. Let's first just kind of talk about the geological processes that we're going to be examining, how this system works in terms of geology. So let's go down to the mantle. We'll look at some peridotite. And in peridotite, there's lutetium and hafnium, about equal concentrations, maybe 1 ppm, something like that. When you melt the mantle material, so you're down here in the mantle, you melt this material, you have magma that rises up into the crust. And let's imagine that we're going to crystallize some magma here in the crust, and it's going to be a granitoid. So there's a separation that takes place in the melting process here, such that hafnium becomes enriched in that granitoid, but lutetium does not. Lutetium tends to stay in the peridotite, whereas hafnium tends to come up with the magma into the granitoid. And then if you look at the different minerals within this granitoid, zircon is really a sponge for hafnium. It really likes that hafnium. So it's going to be thousands of ppm hafnium, but zircon does not like lutetium, so there's going to be very little lutetium. So this is not going to be a very good chronometer, right? We're not going to use zircon, lutetium, hafnium as a chronometer, because look at this, there's a huge amount of the daughter and there's not very much parent. That ratio clearly is not going to change very quickly in time. So everybody okay with that? Just a simple melting process, magma rising upward. Lots of hafnium here, lots and lots of hafnium in that zircon crystal. Let's take a look at a diagram that shows how these values of 176 hafnium, 177 hafnium might change through time. And let's start off kind of like we did with uranium lead to begin with. We're going to start off at the formation of the Earth here 4.5 billion years ago. And let's say at that time we get some crust mantle separation. So we're going to grow some continental crust 4.5 billion years ago. And we're going to see how that crust evolves through time relative to the mantle. Okay, so here goes the mantle. It has a lot of lutetium, right? So the 176, 177 ratio is going to increase through time. You're going to get more and more 176 through time because the mantle does have lutetium. Everybody good with that? Whereas crust down here, it's going to increase a little bit because it has a little bit of lutetium. It has a lot of hafnium, 5 ppm. So the crust is going to change a little bit more slowly than the mantle itself does. And then look at zircon. Zircon down here hardly changes at all in 176, 177. And that's because there's hardly any lutetium in zircon, but there's a whole lot of hafnium. So this kind of shows the three main reservoirs in our system: the mantle, the crust, like a granitoid, and then the zircon. Well, it turns out that if you want to have some kind of a reference to compare samples to, the mantle is kind of hard to characterize and the crust is kind of hard to characterize. It's quite variable. But we do have a reservoir that we can access. You know, geochemists really like this one. It's called CHUR. It's the chondritic uniform reservoir. It's kind of like what the mantle and the crust were together before crust and mantle separated. And we know a lot about the composition of CHUR because meteorites, chondritic meteorites, have that composition. So we're going to use CHUR as our reference, and we'll talk about mantle, which is changing faster than CHUR, and we'll talk about continental crust, which is changing slower than CHUR, and we'll talk about zircon that's hardly changing at all. So here comes kind of a jump. This is the first bump in the road. What we're going to do now is we're going to take this isotope evolution system and we're going to flatten it such that CHUR remains constant through time. Okay. So here's what we're going to do now. Instead of using isotope ratios here, we're going to set CHUR equal to 0. We're going to make that our reservoir. Even though it's changing, we're going to set it to 0 just mathematically. And then we're going to talk about mantle material going up relative to CHUR and continental crustal material going down and zircon going down even more. Even though they're all going up, when you flatten CHUR, some goes up, the mantle goes up, and continental crust and zircon go down. So here's how the world would work in terms of this epsilon notation diagram. Here's the bulk silicate Earth, chondritic uniform reservoir, trucking along through time, but it stays at 0 because that's the way we have set it. Whereas the mantle is going to move positive direction because lutetium is decaying to 176 hafnium. Continental crust is going to not increase as fast as CHUR. So on this diagram, it's going to have a negative slope, and here's zircon way down here. So that's our first bump in the road. We're actually not going to use this diagram, even though this is the way it works in isotope space, isotope ratio space. We're going to do this in terms of epsilon units. And it's just a simple mathematical calculation that takes these variations in the isotope ratio and does kind of like a percent or per mil, but now it's one more decimal place over its epsilon units. And this is just so people can go to GSA meetings and talk about their zircons being -40, -50, instead of having to carry around a number 0.28017. Oh, and yours is 28023. You know, who carries those numbers around? Whereas if it's a plus something or a minus something, those are easy numbers to use. And it also registers everything to this CHR reference frame. So we all can be on the same playing field. So let's go back and look at now maybe a time of melting in Earth history. This is a technique that we always do in combination with uranium-lead geochronology so that we can do these epsilon values as a function of time. So Earth formed here. Let's say that we have a zircon that crystallized 3.7 billion years ago. So here's the uranium-lead determination. Here's the epsilon hafnium analysis that we've done. Of course, we do it at time 0. If we did it 3.7 billion years ago, we would be up here, but right now we're at present day, right? And so what we do is we measure this value present day, and then we can just calculate back how that zircon would have evolved back through time. And that zircon evolution line is going to go back until it hits this DM line. This is the evolution of the mantle. What was previously green going up in space, this is now the mantle evolution line. So this is cool. It tells us we have a zircon that crystallized here 3.7 billion years ago. That's what uranium lead tells us. And the hafnium tells us when we project it back, it hits that DM line. So it says, oh, well, it looks like 3.7 billion years ago, melting took place in the mantle. It produced a granite, and zircon crystallized in that granite. And then it just slowly evolved in terms of hafnium isotopes, very slowly, even though it's a negative slope. Remember, that's because of the CHR flattening. So this tells us something interesting. Well, this is amazing. 3.7 billion years ago, the mantle went through some extraction event where we made some new continental crust. This would be like we use the term juvenile for this. This is different from petrologically juvenile. This is like isotopically juvenile. It looks just like the mantle. Okay, and here's a younger one. Let's do a younger example here. We're crystallizing a granite, a zircon 750 million years ago. It was extracted right from the mantle, and then the zircon evolved along through time, and here's where we measure it today. So slightly positive value of epsilon hafnium, as opposed to an older one, which would give you a negative value of epsilon hafnium. So this is pretty cool. We can use epsilon hafnium values here, just projected back along these evolution lines until they hit DM. And then we can tell great stories about mantle evolution, mantle melting events, crustal evolution, growing new crust, new zircon back through time. And so if the world were really simple, where this is how it always worked, that you melt the mantle and you make a granite, then you could use this hafnium isotope system kind of as a chronometer. It would be the chronometer of when mantle extraction took place, when material was extracted from the mantle, right? So a lot of labs do this, a lot of researchers do this. They interpret the projected evolution path back to DM, and they say, oh, that's when that mantle melting event took place. Unfortunately, this just doesn't happen very often, right? If you know about igneous petrogenetic processes, you really don't get very much granite by partial melting of the mantle. It's usually a more complicated process, maybe a two-step or a multi-stage process. Maybe it's usually something more like this, where you begin to partially melt the mantle. Some of that magma rises up into the lower crust. Maybe it sits there and percolates for a while, mixes with other material. We call this a migmatite or a mash zone. You've probably heard those terms before. Maybe this is what the lower crust looks like. And you can imagine that each of these different components here might have a slightly different age and isotopic history. And now what we're going to do is we're going to partially melt this material and produce this granite. So I think petrologists would say, yeah, that's probably a more likely process than partial melting of peridotite to form granite. Not very common. More likely we're melting this material to produce the granitoid. which also includes this zircon crystal. So it's just adding another step. And so the question is, if you come along today and you analyze the zircon crystal, can you say something about this? Can you say something about when that material was extracted from the mantle? Or can you only say something about this process right here? And the answer, unfortunately, is that there's nothing in that zircon crystal that allows you to say something about this process of melting from the mantle. So here's kind of the bottom line message. It's a complicated process of peridotite going to granite and zircon, and the zircon record tells us a lot about this part of the process, but it does not actually provide information about that mantle melting. So that's kind of bad news. That's what we'd like to know, right? Is what was happening in that mantle evolution time. Let's take a look at this on the isotope evolution diagram and see if we can imagine how we're going to add this complexity. Let's go back to our 700 million year old melting event. We're going to melt some crust here. We're going to produce a new granite body. It's going to have some zircon. We're going to come along and first we'll date it, right? We'll get uranium lead age 700 MA. Then we'll do the hafnium isotope analyses and we'll get a -28 epsilon value for this zircon. What we can do is we can correct back to the crystallization age, just using the lutetium hafnium isotope ratio in that zircon. You can correct back to here. But there's no way that you could correct back farther than that because the zircon didn't exist before 700 million years ago. So there's lots of different ways that we could get to this point right here. One is the very simple way. Maybe it was a one-stage process, and it's the red line. This is when that material was extracted from the mantle. And then you could say, oh, well, mantle melting 2.5 billion years ago, and it just evolved in the mantle through here. And then you made the crust and off you go. Unfortunately, just by making this measurement, you couldn't distinguish the red possibility from the blue one. Maybe you end up at this point here by a 50-50 mix of some slightly younger material and some slightly older crustal material down here in this mash. Or maybe it's an extreme example. Maybe you've got some really young juvenile stuff coming right out of the mantle and some really old material back here. So if you do what people would like to do, the simple thing to project this dashed line all the way back until it hits the mantle, you could get this age for mantle extraction. In reality, it could be blue or it could be green. And the bottom line is you have no idea when mantle extraction took place because you're melting that material from the mash zone, not from the mantle itself. And so that's why we say that the lutetium hafnium system is really not a chronometer. It's not really very powerful unless it's a juvenile system, one stage melting right from the mantle. It doesn't actually give you the time of mantle melting. What it does instead is it serves as a very useful fingerprint for that zircon crystal. And so that's how we use it commonly in the detrital world. You know, for one axis of information would be the uranium lead age that you could do provenance analyses. But if you have a second dimension of information, the hafnium isotopes, now all of a sudden you can do provenance with two different dimensions. And they're pretty much independent. The crystallization time and the epsilon hafnium value, those can be completely separate from each other in that zircon crystal. So we now have two parameters to use for provenance analysis. We have some general terms that we use when we have these measured epsilon values. If you're greater than 0, we commonly refer to this as juvenile, just meaning that it's pretty young crust. To get a point here that ends up here, you can't have a lot of old crust involved, right? It has to be mostly juvenile. Whereas if you have a point that's down here in the -40, -50, you know there's got to be a lot of crust that's at least this old when you project back. It's got to be Hadean or early Archean in age to get an epsilon value down here. So we call this evolved. And then of course, this is where most samples end up. They end up in the intermediate realm where we can't really distinguish between juvenile and evolved. So hafnium isotope values, when you measure them, they provide just the average mantle extraction information, and we can use that as a useful fingerprint. So that's kind of how the system works. Maybe I'll stop for a second and just see if there's any questions that come in on the chat for this.
George, it looks like you have two questions. One is, so the slope for crustal evolution is 0.0113.
Yeah, we can use that. So it's about 0.01, something like that is how we see the average crustal evolution value.
And then the second question you have is, does juvenile mean less mixing?
Let's see, juvenile means that there could be a whole bunch of different, a whole wide range of mixing processes going on in here, but every one of those components has to be pretty young. So that's why we use the term juvenile, kind of as opposed to primitive. You can only be up here if you don't have a lot of stuff from down here. So it doesn't necessarily say it's single stage. It could be right here, or it could be a little bit of this, mix in a little bit of that. Does that make sense? Okay, well, we're going to find out if that makes sense pretty soon. I think first what I want to do is I want to just talk a little bit about the methodology. This is just to help you in case you go to a lab and you participate in the hafnium isotope analyses, so you can understand what's going on with the measurements. And I should tell you that these measurements take much longer and they're much more painstaking than uranium lead geochronology. When you come to a lab, you can probably show up in the morning and they'll do a little fine tuning and adjusting, and maybe by 9:30, 10 o'clock, you'll be off and running, getting good uranium lead ages. You come to a lab to do hafnium isotopes, and you probably will have time to go get lunch. You might even have an afternoon tea break before you're ready to start generating data. Hopefully it happens on your first day and you don't have to spend the whole day watching them tuning and fiddling. But this is a technique that's much more challenging than uranium lead geochronology. And here's why. The natural variations in 176, 177, the whole action is between 28210 and 28220. There's nothing that's smaller than that and nothing that's bigger than that. So the system here operates on this 5th decimal place. So what that means is that you need to be able to make these measurements to 0.01%. We haven't even talked about that yet today, right? We've talked about 1% data. We've talked about 0.1% data for IDTIMs. To do this, you need to be able to measure these values to 0.01%. That's 1 epsilon unit. And the challenge is that if it were just 176 hafnium to 177 hafnium, that would be pretty simple. But the problem is that your mass spectrometer measures 176, and that's a mix of hafnium, lutetium, and ytterbium. And then it measures 177, which is only hafnium. So somehow we need to figure out how to subtract out lutetium and ytterbium and end up just with that hafnium 176. So we call these interferences. Lutetium and ytterbium interfere with the hafnium 176. Fortunately, all three of these systems have pretty similar chemical behavior as they go into the mass spectrometer. So we're not talking about like a 5% fractionation that we did for uranium versus lead. This is more like a 0.1, 0.05% mass bias or fractionation behavior. So if you're ready, let me kind of show you how we do these corrections. What we're trying to do is get hafnium 176. We have to subtract out lutetium and ytterbium 176. Let's do this on an isotope spectrum diagram, just like we did for uranium lead. And remember, the action here is that lutetium 176, this little green one right here, decays to hafnium 176. It's a very long half-life, so there's not a lot of decay that's produced that. So lutetium is pretty small, hafnium's large, ytterbium is large. These are the different isotopes of hafnium, largely 180, 179, 178, 177. These are all stable, naturally occurring. They don't change in nature. 176 is the one that does change in nature. And then in blue, these are the different isotopes of ytterbium. Just from that very first diagram, you can see again, lots of different isotopes here, and this is helpful for us. This is the one we want to get rid of, 176 ytterbium. And then lutetium, we're a little bit limited. There's 175, which is stable in nature. And then there's the 176 isotope here that interferes with the one that we want to figure out. So the problem is that when you do the measurement, say 176 to 177, you get a value that might be 0.4, 0.5, something like that. But what you want is the red to red, 176 hafnium to 177. That's the one that's 0.282 something, right? So here's what you measure, and here's what you want to correct it to, and you have to do that correction down here in the 5th decimal place. So we're starting off with a really huge isotope ratio, making these corrections, and we want to end up at 0.282 with very, very small uncertainty. Just to give you a visual kind of view of the challenge, imagine that you're on one end of a football field and you have a target at the far end, 100 yards away, and your game is to try to hit that bullseye, which is 1 centimeter in diameter. So that's what we mean by 5th place decimal precision here. 1 centimeter, 100 meters away is that 5th decimal place. So the technique for doing this, it's amazing that this works. This was figured out by some really smart geochemists back in the late 1990s, early 2000s. These folks kind of independently, somewhat working together, figured out how to do this. So let me take you through these 5 corrections, and this is just so you understand the complexity of doing these measurements and doing these corrections. So the first factor that we want to correct for is the mass bias of hafnium. And this is just what we said before, the same thing for uranium and lead. Unfortunately, your mass spectrometer always gives you the wrong isotope ratio. You have to be able to correct that isotope ratio, the measured value, to get to the true one. Well, fortunately, 177, 179, these are both stable. Those are stable in nature. That ratio is fixed in nature. We know what this ratio should be. We know 177 to 179. It should have a value of whatever. When you get on your mass spectrometer and you start measuring this, you're going to get a slightly different value. And so what we do is we correct the measured value to the known value. And that's called the hafnium mass bias correction, or beta hafnium. And it's about 1.5% per atomic mass unit, something like that. So here's the first thing we do. This is going to happen in the laboratory, kind of in the background. When you're interested in 176, 177, you're also going to be measuring these other isotopes to be able to get this mass bias. So here's what we do. We measure 177, 179, and then we apply that same correction to 176, 177, because that ratio has also been affected by that mass bias. That's number 1 correction. Number 2 correction is that your mass spec will always give you the wrong ratio for ytterbium isotopes. Fortunately, there's 2 of them, 171, 173, that are naturally occurring and stable. So we know what this ratio should be. We measure the ratio, compare it to the known ratio, and we get the ytterbium mass bias, or beta ytterbium value. And it's also about 1.5% per mass unit. And that's because ytterbium and hafnium behave quite similar geochemically. So we measure 171, 173, and then we apply that ratio to the 173, 176 ratio, and you'll see why we do that in just a minute. Here's our 3rd correction, and this is kind of a tough one. What we want to do is we want to do the mass bias correction for lutetium, but unfortunately, there's only 2 isotopes of lutetium, 175, 176. It would be nice if we had a 3rd one, so we could independently measure that mass bias correction. We can't do that, so what we do is we just assume that it's the same as ytterbium, 1.5% per mass unit. We're going to apply that same correction to lutetium, but it usually turns out okay because there's so little lutetium here that whether we use the exactly right beta value for lutetium is not so critical. Good news for that. So now what we want to try to do is, we're interested in just red 176. How are we going to subtract out the blue? We want to get rid of the blue ytterbium 176. Well, you just measure 173, 176. We know what that ratio is in nature. And so if you know 173, you know the ratio, you can just subtract out how much 176 there is. Good news. Now we only have red and green to deal with. And so here's our 5th correction. We measure 175. We know the 176, 175 ratio in nature so that we can subtract out the amount of 176. And so voila, at the end of these 5 corrections, we've got 176, which is just hafnium. And now we can do that ratio of 176 hafnium to 177 hafnium. How does that sound? Those corrections make sense? So you have to do all these different isotopes. You can only do this with a multi-collector mass spectrometer. There's just too much precision required to do this with a single collector. So you have to have a multi-collector mass spec, and have to have enough collectors to go 177 all the way to 180 here. So 10 different Faradays, and you have to calibrate them really well to be able to do this. Okay, well, let's just talk a little bit about the measurements, and then we'll look at some data and see how we're going to use this information. The setup is exactly the same. It's a multi-collector mass spec. Laser fires away, it drills a hole into the zircon. We usually use a larger spot, about a 40 micron spot. We'll drill down a little bit deeper, maybe 25, 30 microns deep, and that's just to gather enough ions that we can get the precision that we need for hafnium isotope analyses. The way that we check that we're doing these corrections correctly is by putting a solution into our mass spec. So this is a little bit challenging. Most laser ablation systems are set up just to have a solid material analyte coming in from the laser ablated material into the torch. Now we have to have a setup where we can put some solution in there. And we do this with a magic formula here, JMC475. All labs use the same formula. We know what that ratio is, 28216. Plus or minus 5 in the fifth place out here. And now what we're going to do is we're going to take some of that JMC 475. It plots right here on the x-axis. And so here's just a set of data from one session. You can see, oh, good news, we're kind of average about 28216. I'm going to take that JMC 475 solution, and I'm going to intentionally add some ytterbium and some lutetium solution to that cocktail. And then I'm going to analyze it with the mass spectrometer. And so I'm going to get some ratio here that's measured from that cocktail, which is huge, right? 0.3, 0.4, 0.5, something like that. And then if I do all these corrections correctly, I'll be able to get that JMC value back to 28216, regardless of how much ytterbium and lutetium I have. Even if over half of the ytterbium, even if over half of the 176 is ytterbium and lutetium, I still need to get down to this 28216 value. So this is the challenge that when you're talking with a lab about coming to do hafnium isotope analyses. This is the plot you want to see. You want to ask them to show you the JMC 475 plot and look at the cocktail. Anybody can measure 28216 just on JMC 475. It's the cocktail that's tough. It would be like taking this measured value and you're about a mile up in the air in ratio space, and you're correcting it down to this 28216 value to 0.01% precision. So that's the challenge. Well, great news if you can do this for solutions. That's the first kind of hurdle that you have to get over. But we probably should look at zircons, right? We probably should put some standards onto our mount and see if we can reproduce values that are known for those other zircon standards. So this is what we do. These would be the unknowns that we want to analyze. And now instead of just one standard or two standards, we use all these different standards, and these have been calibrated by solution ICP-MS. So we know what the true values are. FC1, you know about that, Plisovici, 337 MA, 91500, kind of a classic standard for isotope geochemistry. All of these are different standards that have been calibrated for hafnium. And you want to put them all on. You want to have them on the same mount that your unknowns are to make sure that the calibrations you're using apply not just to the standard mount, but also to the unknowns. And then here's what you want to do, exactly the same that we did for the solution. If your zircon does not have any ytterbium and lutetium, you're sitting here at 0. And so there are some zircons that are like that. Mud tank is a classic zircon. Labs love to use mud tank as their standard because it doesn't have any lutetium and ytterbium. You almost always get the right answer for mud tank, but that's easy. These are a lot more challenging, R33 and Temora, those two here. They have a lot of ytterbium and lutetium. Your unknowns probably do also. And so what you want to be able to show in the lab is that you can measure for R33 and Temora, FC1, and get all of those down to the known value. This line should be straight. So this would be the second plot that you'd like to see from the laboratory. Show me your standard plot, and you want to be able to see that these are perfectly straight lines. If any of those corrections are not being done quite right, the slope will not be horizontal, and then you'll have a bias in your data. The more lutetium, terbium you have, the farther you are off from the right hafnium isotope value. So this is all about standard calibration. This is the really time-consuming part. Kurt and Sarah jump in, but I think we probably spend more time running standards and calibrating than we actually do on the unknowns. We might spend a whole day, your first day in the lab might be a whole day of running those standards. And then if you're lucky on day 2, off you go with your unknowns. Well, sometimes it's better than that. Here's how the analysis works, just like Kurt was showing you for uranium lead. Now we take a long time on backgrounds. We're just sitting here counting, trying to get those background values really precise. You fire the laser and you drill, in this case, for about 60 seconds. I think we're more like 40 seconds right now. And look at the number of ions, 100 million atoms coming out of here per second. So you're ablating a lot of material, getting a lot of ions. You need a lot of ions to get that 5th place precision. 180 is the largest. These are the different hafnium isotopes. This is the one you want, right? 176, but this is the bad news. It's not just hafnium, it's also a terbium and lutetium. These are the other ones that you measure to be able to do those 5 calibrations. So this is the action 176, 177, but to do it, you have to measure all those different isotopes at the same time. We're getting near the end here. We're going to look at some data in just a minute. Let's just kind of go through the 2 possible examples. So here's for a juvenile zircon. This is the kind of workflow. You would measure some value. It's going to be like a mile up in the air, 0.4, 0.5. You do those 5 corrections. If you do them right, you end up down here, which is the true 176, 177 value for hafnium present day. Then you use the 176 lutetium, 177 hafnium ratio. That tells you how much lutetium is in there. That's the slope of the red line. You correct back to the crystallization age. And if you end up right here on DM, that would be the age of mantle extraction. So here it is in isotope space. Here it is in Chur or epsilon space. Correction, measured value, correction back from the lutetium evolution, you end up on DM. Well, that's a cool story. 3 billion years ago, we had extraction of magma from the crust, and that zircon records that mantle extraction process. Well, unfortunately, that doesn't happen. I would say maybe 10% of our analyses sit on top of DM, and usually they sit off somewhere like down here, down in the middle of epsilon space. And so here's what you're going to do. You're going to measure the value, 5 corrections, you get to the present value, you back correct for lutetium decay, and you end up right there. And the question is, how did you get there? Maybe it was 1 stage melting, and then you just project back until you hit DM. You're kind of making it up though, because you're before the crystallization age. This is all happening before that zircon formed. So you're just kind of making this up. But you can also get to this point by a mix of purple and black, or juvenile and way down here. So you have no idea how you ended up at that spot. And this is the ambiguity. This is why you can't project that line back to here and talk about this mantle extraction age for that zircon crystal. You can't go back earlier than the crystallization age because there is no record in that zircon crystal. All right, so let's see if you've got this figured out. Sarah's going to take over from here. I'm going to leave you with kind of a thought experiment where we've done the uranium lead geochronology. This is the PDP or the histogram that you have from your sample. This is nice. This would be like, this looks like North America to me. There's a 1 billion year old. This would be like Grenville. 1.4 is the anorogenic granites. 1.7, 1.8, Yavapai, Mazatlan province. Maybe a little bit of Archean coming from the Superior province or Wyoming province. This looks like a good age distribution for North American zircon. Now let's look at what the hafnium isotopes would tell you from those same zircons and see if we can say something interesting about the evolution of North America. So I'm going to stop sharing now, unless there's a question about this.
Yeah, George, we got a question.
Yeah, let's have some questions.
Okay, so 176 lutetium changes to 176 hafnium, as you've outlined. So what about 175 lutetium to 176 lutetium? How about that ratio? Would that change through time? And is there a problem with that?
Back here. Fortunately, no, there is no decay of anything else to lutetium-176, nor ytterbium-176. So this ratio, 176, 174, that's fixed in nature. 175, 176, that's fixed in nature. If that were not the case, game over. You couldn't do this. The method only works because all of these ytterbium isotopes and all of these lutetium isotopes are stable. The only radiogenic daughter product is 176 hafnium. I hope, was that the question that was answered, was asked?
It was about the ratio of 175 to 176. If 176 lutetium is decaying, would it be changing that ratio?
Yeah, but you're doing this just at present day, right? All of these things are at present day. So we know what the modern world 176, 175 lutetium value is. Yeah, good question. Just like for uranium lead, we know what the 238, 235 value is, 137.82. Fortunately, that's fixed in nature. If that were not, then, oh, you couldn't do 206, 207 ages. Okay, so I'm gonna stop share and I'm gonna have Sarah come on and she's gonna take us into use of hafnium isotope data.